This video is on Unit 5, Chapter 11, Graphing and Solving Rational Functions, Lesson number 1, Graphs of Rational Functions. In your notes here, it says that a rational function is a function of the form f of x is equal to p of x divided by q of x. Now, p of x and q of x are polynomials, and q of x, because it's the denominator, cannot equal 0. Steps to graph. We've got several steps here that we're going to go through to graph these rational functions. Step number 1 says to simplify the function. And then what you're going to do is you're going to use that simplified version to go through the rest of these steps. Step number 2 says find the x-intercepts by setting the numerator equal to 0. Now remember, your x-intercepts are also the zeros or the roots of the function. In step number 3, we're going to find the vertical asymptote by setting the denominator equal to 0. As another reminder, an asymptote is a line in the graph where the function cannot cross. So it approaches that line but does not cross that line. Step number 4, you're going to find your horizontal asymptotes using the rules below. So when we look at these rules for horizontal asymptotes, we have to pay attention to the degree of the numerator compared to the degree of the denominator. And the degree comes from the exponent. So you look at the highest exponent in the numerator and compare it to the highest exponent of the denominator. If the degree of p, which is your numerator, is greater than the degree of q, which is the denominator, then there are no horizontal asymptotes. So again, I'm going to put a little 1 here for case number 1. And then for case number 2, if the degree of the top is less than the degree of the bottom, then your horizontal asymptote will actually be your x-axis, where y is equal to 0. That's the equation y equals 0. And in the third case, if the degree of the top is equal to the degree of the bottom, then what we have to do at that point is divide the leading coefficient of the numerator by the leading coefficient of the denominator, and that will give you your horizontal asymptote at y equals whatever that is. And then lastly, in step number 5, we're going to identify any holes. Now, holes in our function are created when we have common factors. So it says here, what is a hole? A hole is a point, so it's an ordered pair, x, y, at which there is a break in the graph. A hole occurs where there is a common factor between the numerator and the denominator. To find the x-coordinate, you're going to set the common factor equal to 0. And then to find the y-coordinate, you're going to substitute that x-coordinate into your simplified function. I'm going to walk you through all of these steps. Let's first look at example number 1. The directions here are telling us to graph each function and identify its key characteristics. So step number 1, again, is telling you to simplify. And in example number 1, there is no factoring that we can do. There's no simplifying that can be done. So step number 1 is already done. So in step number 2, we are going to find the x-intercepts by setting the numerator equal to 0. So the numerator is our x minus 4. We're going to set that equal to 0. Add the 4, get x equals 4. Now your x-intercept is a point. It's an ordered pair. So at 4, 0, our function is going to hit the x-axis. So again, just a reminder, that is a solution. So x equals 4 would be a solution if we were solving this. Moving on to step number 3. Step number 3 says to find the vertical asymptote by setting the denominator equal to 0. So the denominator is x plus 4. Set that equal to 0. 4. X equals negative 4. Now, your asymptotes are lines. So we want to make sure that we write this in the correct format. X equals negative 4 is the correct format for that. It's a line. So I'm going to represent that with a dashed line. Find x equals negative 4. And that vertical line going through x equals -4 is our vertical asymptote. In step number 4, to find our horizontal asymptote, we're going to use those rules. So the degree of the top is 1 because that's the exponent. The degree of the bottom is also 1. So they're equal. That's going to be case number 3. When the degree of the numerator is equal to the degree of the denominator, our horizontal asymptote is at y equals the leading coefficient at the top is 1. The leading coefficient at the bottom is also 1. So we get y equals 1 for our horizontal asymptote. So y is equal to 1 is here, and horizontal line going through that is where we can find our horizontal asymptote. Step number 5 is our holes. Now, again, a hole is created when you have common factors that you cancel, which we didn't have any in this example. So I'm just going to write none. There are no holes in this function. Now I'm going to look at the graph. So I'm going to go to y equal on my calculator, and I'm going to put in this x minus 4 divided by x plus 4. Now, one thing I haven't said to you yet is, or I mentioned it already, but when you are following through the steps 2, 3, 4, and 5, always make sure that you are looking at the simplified version. Now, in this example, our original problem, which was our x minus 4 over x plus 4, it didn't simplify. So when we go to the calculator, when I put this function into my calculator, I want you to go back to the original version, which for this example is the same thing. But the original version, x minus 4 over x plus 4, I'm going to pull up a fraction in my y equal. And again, I'm going to plug in my x minus 4 over x plus 4, and then I'm going to load the graph. So looking at my graph, this is doing exactly like what most rational functions do. And you have two branches, and those two branches are created by that horizontal asymptote and your vertical asymptote. Sometimes there are slant asymptotes. In Algebra 2, we are not going to focus on those slant asymptotes. You will learn more about slant asymptotes when you get to pre-calculus. But we can see our vertical asymptote, which was x equals -4, sorry. You can kind of see it right here. And that blue graph, the graph of the function, would approach that. Let me zoom out just a little bit. Let me zoom out. And here's your x equals -4. Again, you can see that that's going to approach that line, both in the upper part and in the lower part. Same thing with our horizontal asymptote. Our horizontal asymptote was at y equals 1. And you can see that, again, that's going to approach that line. So from here, all I'm going to do is I'm just going to sketch this. We had upper left and bottom right. Oops. Now, if I wanted this to be a little bit more precise, I could certainly go to my table of ordered pairs, and I could make this look a little bit better by finding some ordered pairs that hit nice and pretty. But I really just kind of care about the fact that you know what a vertical asymptote is, a horizontal asymptote, you know about your x-intercepts, your whole, things like that. Now I want to look at domain and range. So for the domain, remember that the domain is your set of x's. So I'm going to highlight my x-axis here. Remember that your x-axis, your domain, goes from -infinity to +infinity. So we're going to go left to right on the graph here. As we move left to right, I'm going to follow my function here. Um, as I follow it left to right, I have to pick up my pencil at that vertical asymptote and then come down here to the bottom to continue following along with that function. So your domain is actually going to include all x's except for your vertical asymptote. So I'm going to write this in set builder notation versus interval notation. And what this says is that your domain is the set of all x's such that x cannot equal -4. And the reason for that is because that's where your vertical asymptote is. Now let's talk about range. And then remember, range is your y's. And again, I'm going to highlight the y-axis here. So we're going from negative infinity on the y-axis up to positive infinity on the y-axis. Again, following this function from bottom to top, drawing my pencil, marking my pencil along the graph. Once I get over here, I have to pick up my pencil and come back to continue on the function. So it's going to include everything going down to negative infinity and up to positive infinity, except for that horizontal asymptote. So it's going to include all y's except where y is equal to 1. So there's example number 1. I want to look at example number 3. In example number 3, we have some reducing that we need to do. We have some simplifying that we need to do. Again, step number 1 is going to tell you to simplify. I'm going to factor my numerator. This is the difference of squares, and I factor into x plus 1 and x minus 1. Then I have my x minus 1 in the denominator. Now, in this instance, we have common factors that we can simplify, and this becomes f of x equals x plus 1. So that's my step number 1. I've got it simplified. Step number 2 is going to tell you to find the x-intercepts by setting the numerator equal to 0. So I'm going to take my numerator. You'll notice here, we've simplified this. Again, this is what you're looking at. You're not focusing on that original equation at all whatsoever. You only have a numerator. You don't have a denominator, which is going to come into play here in just a second. Take that numerator, x plus 1, and I'm going to set it equal to 0. Subtract the 1. We get x equals -1. So there is your x-intercept, -1, 0, which, again, as a reminder, is also a root or a solution of the equation. Okay, so that's my x-intercept. Step number 3 is going to tell you to find the vertical asymptote by setting the denominator equal to 0. Well, again, you don't have a denominator here in that simplified form. So we have no vertical asymptote. And then in step number 4, it's going to ask you to find the horizontal asymptote using those rules. Now, the degree of the top is 1. The degree of the bottom, because there is no bottom, the degree of the denominator is 0. So when the degree of the top is greater than the degree of the bottom, that's case number 1. The degree of P is greater than the degree of Q. There is no horizontal asymptote. Again, none, because there is no horizontal asymptote. All right, so let's put this into perspective. There's no vertical asymptote. There is no horizontal asymptote. So there's no restrictions on this function. And so there is one restriction. Let's talk about a whole. Anything that you cancel, which is your x minus 1, we're going to set that equal to 0 to find where this whole is. Add the 1, and you get x equals 1. Now, a whole is an ordered pair. So my whole is at 1 something. I'm not sure what that y coordinate is. To find it, you're again going to go back to that reduced form, and you're going to substitute in what you got So we're going to find f of 1. 1 plus 1 is equal to 2. So y is equal to 2. At 1, whoops, at 1, 2, there is a hole. All right, so from here, what I want to do is I want to quickly look at the graph of this. Now, remember, when you go to put it into the calculator, go back to the original 4 minus 1 divided by x minus 1. I'm going to hit fraction x squared minus 1 over x minus 1. And I'm going to hit graph. Now, what you're going to notice here, I'm going to hit, let me hit zoom 6 to pull it in a little bit closer. This is a straight line. It's just a linear equation. And the reason for that is because, again, I said a second ago, there's not a horizontal asymptote to restrict this or a vertical asymptote to restrict this. The only restriction that we have is the hole. Now, unfortunately, on this graph, we can't see the hole. If you look at the table of ordered pairs where x is 1, you're going to see error. Again, that is because at that point in the original problem, if that x equaled 1, then it would create a 0 in the denominator, making that point undefined. But because it canceled, it just creates a hole and not an asymptote. So let's go back and let's graph this. When you go to graph this, again, right here, you can pick up some points if you want to. 0, 1, 2, 3, 3, 4, 4, 5. Or it is just a linear equation, y equals mx plus b. So it crosses the y-axis at 1 and has a slope of 1, up 1, right 1. And then you can draw your line. Now, domain and range. Again, looking at your x-axis for the domain, it's going to go forever left and forever right. But if you follow the line left to right, do you ever have to pick up your pencil? Yes, you do. You have to pick up your pencil when you get to that hole. So that creates a point where x cannot equal something. So I want to write this in, again, set builder notation. It's the set of all x's, but x cannot equal 1, and that's where my hole is. And for your range, bottom to top, again, it's going to go all the way from negative infinity to positive infinity, except for where we have that hole. You have to lift up your pencil. So it's all the y's except for where y is equal to that 2. All right, one more. Let's look at example number 4. In example number 4, f of x is equal to x plus 5 divided by x squared plus 9x plus 20. Again, in step number 1, what we want to do is we want to factor anything to the factors. So top good. We're going to factor bottom. I need two numbers that multiply by 20 to add, give me 9, positive 4, and a positive 5. Now my x plus 5 is going to cancel, leaving me with f of x equals 1 over x plus 4, because our x plus 5 cancels. That's step number 1. In step number 2, we want to find our x-intercept by setting the numerator equal to 0. Now, again, one more time. Remember that in step, oops, I thought I hit my highlight. Sorry. Steps 2 through 5, you are only looking at that simplified form of your original function. So the numerator doesn't even have an x in it, which means that there is no x-intercept. So there's no real solutions for number 4. It doesn't hit the x-axis, so there are no real solutions. Step number 3, you are to find your vertical asymptote by taking the denominator and setting it equal to 0. A denominator is x plus 4, set it equal to 0, and solve. We get x equals -4. So my vertical asymptote is at x equals -4. I'm going to find -4 on the x-axis, and I'm going to draw that vertical line. I'm going to use the dash line again for that vertical asymptote. In step number 4, using your rules for horizontal asymptote, the degree of the top is 0 because there's no x. The degree of the bottom is 1 because there's an understood 1 exponent on that x. So the degree of the top is 0, the degree of the bottom is 1. So the top is less than the bottom, which is case number 2. The degree of P is less than the degree of Q. The x-axis is our horizontal asymptote, which is our y equals 0. So that's our x-axis. Now, in step number 5, we want to find our whole. Again, your whole comes from anything that reduces out, which is our x plus 5. So x plus 5, set it equal to 0, minus the 5, and you get x equals -5. So my whole is at -5 something. You have to substitute that back into that reduced form. So f -5 is equal to 1 over -5 plus 4. So I get 1 over -1, which is -1. So at -5, -1, there's the whole. Now, to graph this, I don't even really need to graph it. Because my whole is down here, I know that one branch is on the bottom left, the other branch is going to be on the right. Let's go ahead and look at it. Y equals, clear this one out, fraction. We've got x plus 5 in the top, and x squared plus 9x plus 20 in the bottom, and then I'm going to hit graph. Zoom 6. Now, the cool thing here is, for whatever reason, you can actually see the hole that was created here at -5, -1. So you can also identify the fact that there's a vertical asymptote, there's also a horizontal asymptote, and you can see your hole. Now, again, from here, if you wanted to make this a little more accurate, you could grab some ordered pairs from your table, or I'm just going to quickly sketch this function. Okay, so there's my sketch. Now let's talk about domain and range. Left to right for domain, again, is your x-axis. Left to right, it's going to go all the way to -infinity, and it's going to go all the way to +infinity, but there are a couple of restrictions here. So as I move left to right, I've got a whole and a vertical asymptote. So it's going to be all of my x's except where x is equal to -4 and -5, because that's my whole and my asymptote. The same thing's going to happen for your range, which again is your y's. Bottom to top, I'm going to go up. I'm going to hit that hole. I've got to lift my pencil. I've got to lift my pencil again to continue along this function. So it's all of the y's except y cannot equal -1 or 0. So 0. All right. So those are the examples that I have for you for this lesson. Lesson number 1 in chapter 11 on graphing rational functions.